Here is a funny way to think about projections. Imagine this green vector as the ground. Yes, I know it's not horizontal, we're just looking at it from a different angle. This red arrow is just some object that is drilled into the ground. Okay, now when the sun shines on it, you're going to get a shadow, right? And that shadow vector is the projection of the object onto the ground. To be honest, I don't know if shadows actually behave like this. Bruh. But that is how vector projections work. You're projecting this red object onto the ground. In other words, you're projecting the vector u onto the vector v, and the resulting vector is parallel to v, just like how a shadow is parallel to the ground. Let's look at the case where the angle between the vectors is acute. So the sun will shine and you'll get the shadow. We just projected the image of the object onto the ground, or projected u onto the vector v. Another way to understand projections is through this one phrase. The projection of u onto v is the component of u parallel to v. Notice that the projection is always parallel to the vector v that you're projecting onto. And it's also a component of u because the projection plus this blue vector adds up to give u. To prove the projection formula, you just need to know what theta means in the dot product formula. Theta is the non-reflex angle. A reflex angle is just an angle bigger than pi radians. Notice that this only works when you take u and v starting at the same point. On the left, we have theta being obtuse, which means the cosine of theta is negative, and that means the dot product is negative. But when theta is acute, we have cos theta being positive, so the dot product is positive. Keep that in mind. Let's prove the projection formula for the acute angle case first. In this right angle triangle, cos theta gives this expression because it's adjacent over hypotenuse. Also, cos theta is u dot v over the length of u times the length of v, just by rearranging the dot product formula. We know that the projection vector is parallel to the vector v, so it's k times v for some positive constant k, which we're going to try to find. So if we take lengths, noting that the absolute value of k is just k, since k is positive, we get this. Substitute this in and solve for k, and then remember that the projection is k times the vector v, and there you go, we have our formula. What's cool is that the formula still holds even if the angle between the vectors is obtuse. Note that this angle is pi minus theta. So we can use right angle trigonometry again, and you should know that cos pi minus theta is minus cos theta. You should memorize that, but you can prove it with the angle sum identity. Okay, then we just substitute in the dot product expression, rearrange, and use the fact that the projection is k times the vector v. K is negative in this case. So when we take absolute values, the absolute value of k is actually negative k. Sub that in, and you see the negatives cancel. The last few steps are the same as before, and there you go, we have our formula. If you enjoyed this video, please consider subscribing. It's completely free, and it would be great if we could get to 200. Thank you.